Well, thank you very much, Donna and Mark, for hosting us today. I really appreciate the opportunity to talk about Microfluidizer and how it works well with the particle sizing systems, particle size analyzers. Just a quick note about the agenda for today and cadence. Basically, I'm going to start talking about Microfluidics, the company, and Microfluidizer technology. Then I'm going to pass it over to Mark, who's going to talk about his particle size analysis capabilities and the technology. And then together we're going to talk about some applications that we've developed together on the Microfluidizer and with the analysis on the PSS Nicomp. So just real quick, a little bit about Microfluidics. We were founded in 1982, so we've been around for 36 years, selling microfluidizer processors globally. We were acquired by IDEX Corporation about 6 years ago and put in a group with Quadro Engineering, the Fitzpatrick Company, Matcom, to form this material processing technologies platform. So Microfluidics is very familiar with nanotechnology applications, but if you have any other material processing questions, we have the support of a full platform behind us, and feel free to let us know because we have a lot more expertise than just nanotechnology. Microfluidizer processors are used for both R&D and manufacturing of many different types of materials, primarily in the biopharmaceutical industry, but we also work a lot with chemical industry, cosmetics, and food industries. Microfluidics' core competence is really two things. One is we have a lot of experience with process development of nanotechnology applications. We also have a lot of experience with design of equipment for cGMP manufacturing. So those are the two ways that Microfluidics can help our customers bring their applications to the market. So this is just a little bit about what we do best from an application standpoint. Our primary applications are nano-emulsions and cell disruption, but we also have a lot of experience with polymer nanoparticles, liposomes, and we do some work with particle size reduction, deagglomeration, and in some cases we can even do molecular weight reduction. So what is special about a microfluidizer processor? Microfluidizer processors can ensure that every milliliter of material sees the same high shear condition, processing conditions. And that means that we can generate nano-emulsions that can be sterile filtered. We can do cell disruption with the highest levels of protein recovery. And we can do particle size reduction and achieve very narrow distributions. So how do we do that? This is a schematic of a microfluidizer processor. It's a very simple idea. One of the cores is that it has a constant pressure intensifier pump. And this ensures that all of the material that is processed at the same pressure. Talk about that a little bit more in a minute. And the other key principle is we have a fixed geometry interaction chamber. And that concept of the fixed geometry is also critical to achieving uniform processing. These are custom-made pumps. So they can pump tricky materials like things that are very viscous or materials that have high solid loadings. And we can also work with a very wide range of temperatures. We can work with a wide range of solvents. And virtually all of our equipment has some sort of energy removal device like a heat exchanger or a cooling coil or something like that, because temperature is often a critical processing parameter in many applications. This is the schematic of our interaction chambers. This is what they look like on the inside. These are just cartoons, but essentially we have two different types. This type on the left is called the Y-type interaction chamber. What happens is the material comes in through the top and is forced to split into two streams, and then those two streams impinge upon each other in this high shear zone. These Y-type chambers are typically used for emulsions and liposomes and other mixing applications where it's critical that mixing is extremely thorough. So when you're making a nano-emulsion, what you do is you generate extremely small particles, and then those small particles have very high surface area. That high surface area causes instability. And in order to mitigate that instability, you need to have a surfactant available at the surface very quickly, or else the droplets will coagulate. So that high level of mixing prevents that coagulation from occurring. The Z-type chamber is a little bit simpler. There is only a single path. There's still this high velocity area, but the impact force is against the wall. So that is typically used for breaking applications like deagglomeration or cell disruption, or if you're just trying to reduce particle size. These chambers are made out of either ceramic or diamond, so they are very resistant to abrasive forces. And they come in many different sizes, so 2 different shapes, but several different sizes. And the nice thing about having a fixed geometry interaction chamber is that you can calculate and control the exact shear rate at which you are processing. So this is the velocity profile inside the high shear zone. So the material comes in, this is a cross section. It is accelerated across through this high velocity zone, and the velocity profile looks like this. And in order to calculate shear rate, we use the maximum velocity, which is in the middle, minus the minimum velocity, which is the velocity at the wall. We assume to be 0. And then the critical dimension is half the height of the microchannel. So for instance, a typical calculation might be something like if you have a height of, say, 100 microns, the critical dimension would be 50 microns. If you have a velocity, say, 400 meters per second, that would result in a shear rate of about 8 million inverse seconds, which is extremely high relative to most other high shear technologies available. But we can also achieve a specific shear rate by varying 2 variables. Number one is the pressure. So you can work with different processing pressures to achieve different shear rates, but you can also vary the size of the microchannel to achieve different shear rates as well. So for many applications, customers want to work with the highest shear rate possible, but there are other applications where it's much more critical to achieve a specific shear rate in order to achieve the desired results. The other thing that's really nice about having fixed geometry microchannels is that scale-up is very easy. So these are the lab scale chambers. They only have a single microchannel. When we go to scale up, what we can do is we can put these microchannels in parallel and arrange them inside a single interaction chamber and achieve higher flow rates at the exact same shear rate. So if you develop your process on the lab scale, and typically the process parameters that you would optimize would be the processing pressure, the type of interaction chamber, the number of passes. And when you do that, you can replicate those exact particle size reduction conditions on the production scale, and typically you can achieve the exact same results. So scale-up is virtually guaranteed. So why is uniform processing important? It's important for different applications for different reasons. For emulsions and liposomes, when you achieve uniform processing, you are able to get these very nice, small, uniform particle size distributions. And that results in a great deal of stability. And also, the microfluidizer is the best technology for processing nano-emulsions if you want to do sterile filtration afterwards, because this uniform particle size will fit through a sterile filter very easily. For cell disruption, the idea is you want to break as many cells as possible at the lowest energy input. So you can tune the microfluidizer processor to a specific shear rate that breaks the cells at the lowest energy level, and then the proteins that are released are intact and they're not denatured by elevated pressures or temperatures. And for dispersions, typically people want very narrow particle sizes. For instance, if you're processing an active pharmaceutical ingredient, a small, narrow particle size will have a very predictable delivery rate in the body. So people often ask what distinguishes the microfluidizer from other types of high-pressure homogenizers. And really the answer is this fixed geometry interaction chamber. Homogenizers typically use a homogenizing valve, which opens and closes. So what that means is that critical dimension is always changing throughout the process. The other factor is the pressure profile. For a microfluidizer, we've already talked that we use constant pressure pumps. So this green pressure profile is a microfluidizer. And you can see that as the piston moves forward, it quickly achieves the desired processing pressure. Virtually all of the material is processed at the desired pressure, and then it quickly drops back down to zero, and then at 0 psi, there's obviously no flow, so no material is processed. With a homogenizer pump, it is a constant volume pump. So although the homogenizer might claim to be able to achieve 30,000 psi, only a small fraction of the material is actually processed at 30,000 psi, and then a lot of the material is processed at lower pressures. When we talk about shear rate, so for the microfluidizer, the shear rate is directly proportional to the pressure because that dimension never changes. Whereas with a homogenizer, when that valve opens, the shear rate quickly drops because that dimension is much larger than when it's closed. So even though the pressure might be high, the shear rate is actually lower because that critical dimension is so much lower. So this is what the flow rate profile is. Again, for the microfluidizer, it's only dependent on the pressure. For the homogenizer, it is a fixed volume per stroke flow. So you get this sinusoidal-like flow rate profile. But what does this all really mean? It means that you get different particle size distributions even at the same processing conditions. So this is some particle size data from processing a liposome. One is through a microfluidizer processor, the other is through a high-pressure homogenizer. Both are processing at 30,000 psi, and you see that with the microfluidizer processor, you get these nice unimodal particle size distributions that are in the range of around 100 nanometers. Whereas with the homogenizer, you get multimodal distributions because some material is processed at high pressures, but some material is also processed at low pressures and low shear rates, and the particle size is much larger. So just a quick summary, the microfluidizer technology is different because we use constant pressure processing with very high potential processing pressures. We have fixed geometry interaction chambers, and they can be multi-slotted for scale-up. And this means that we can achieve very small particle size with consistent processing resulting in narrow particle size distributions, excellent batch-to-batch repeatability, and guaranteed scale-up to the production scale. All right, so with that, I'm going to switch over to Mark, who is going to present about the PSS technology.
Thank you, Steve. So what we're going to do now is talk about the analytical particle size analysis techniques offered by particle sizing systems, and then show data that we use to monitor the microfluidizer process. There are two technologies we're going to talk about today. The first one is dynamic light scattering, or DLS. If you're not familiar with this principle, you see the cartoon in the upper right. This is a particle being bombarded by the black dots, which are water molecules. So the yellow particle is moving in a random thermal motion due to the interactions with the water molecules. This is Brownian motion, and Brownian motion is dependent on the temperature, the viscosity, and on the size of the particle. So what we see here in this little diagram of how a DLS instrument works, we have a light source. We place the sample here. We have a detector at some angle, in this case at 90 degrees, and we're just picking up on the change of light scattering at this 90-degree angle due to the motion of the particles. The detector then feeds the photon count rate into a device called the correlator. The correlator looks at the change in count rate as a function of time. Small particles move more quickly, large particles move more slowly, and we build up this correlation function. From the correlation function, we can calculate d, the diffusion coefficient. Then using this equation, we can calculate for r, the radius or the diameter of the particles. So all we really need to know about DLS, it's a very simple technique to use. We just place a sample in the chamber. We look at the change in the rate of light scattering and calculate the particle size. This is the Nicomp instrument that we used for collecting the data that we will show later in the presentation today. And we can configure the instrument several ways depending on the requirements of the application. We can build it so it's only for particle size, or we can also add zeta potential. We may be interested in the surface charge of particles when we get down to these small sizes. We can build it so it either has the detector at a fixed 90 degrees, or we can have a multi-angle goniometer where we can adjust the angle to optimize it for different kinds of samples. We can use different lasers and detectors depending on how small are the particles, what kind of scattering properties do the particles have that we're going to measure. A unique feature is we can actually put an auto dilution unit onto the system for when we're working with systems that are high concentration. We can automatically dilute those samples. If we're working in an environment where we need high throughput, where there are many samples that require analysis, we can add an auto sampler onto the system. In the picture you see on the right is showing actually an online system, which is DLS. This one is also a combination of DLS and single particle optical sizing. So if we need to do online process monitoring, we also have an online system we can use to continuously measure particle size using dynamic light scattering. One of the unique features in the Nicomp DLS system is the algorithm we use to see if there's more than one peak in the distribution. So essentially there are two approaches to calculating the final result. We can assume a Gaussian distribution, which is by definition a symmetric unimodal distribution. But then there's a calculation in the system, which is this chi-square, and it tells us if that number gets higher, perhaps we should look at the Nicomp distribution. And we see here where we had a mixture of 100 and 170 nanometer polystyrene latex spheres, where we actually split it and got a fairly accurate representation of the two different sizes. To the right, we see the same case where we actually took a mixture of polystyrene latex particles at 150 and 200 nanometers. If you used a Gaussian result, you'd meld those two into a single peak, but what you see up above is the ability to separate these peaks. And this is the ability of the Nicomp to catch, perhaps you have a population of single particles and then you have aggregates or agglomerates. And the system is capable of detecting where these peaks are with much higher resolution than other instruments that are based on dynamic light scattering. So this is one of the unique capabilities of the Nicomp DLS system. Dynamic light scattering works basically from about 1 nanometer to 1 micron, maybe a little larger for emulsions. And that's the technique we're going to use for seeing most of the results today. But what if we had a few large particles out here at several microns? Well, then we might use a technique which is known as single particle optical sizing, or SPOS. This is an optical sizing technique where one at a time the particles pass through a light source. And as they do, we have two detectors. We look at the extinction, essentially the shadow cast by the particle, and we look at the scattering from the particle light interaction. We take these two pulses, feed them into a pulse height analyzer, and then through the use of a calibration curve, convert pulse height to particle size, and one at a time count and size these particles. So this is our LE400 sensor, which has these two detectors, extinction and scattering, where the light beam is uniform, it's collimated. The next advancement we've made to these sensors is the AccuSizer FX series, where we focus the laser beam. So here, instead of a collimated laser beam, what we're doing is we're focusing that laser beam. And we're going to look at the particles passing through the very center of the cell here. And what this does is it essentially reduces the inspection zone, and when we reduce the inspection zone, then we increase the concentration limit we can work at, because we only want one particle at a time interacting with the light source. So we can increase the concentration limit of the technique by focusing the laser beam. Now when we use this technique, the dynamic range is about 0.7 to 20 microns, but now we can work up to the scale of 1 million particles per ml, whereas the LE400 sensor works on the scale of 10,000 particles per ml. So this is when we used a focused laser beam and we look at the extinction signal from the particle interaction with the light source. The next development in sensors is the FX Nano sensor. Again, we're focusing the laser beam, but here we're mostly looking at the light scattering. We have an extinction and a scattering detector in the sensor, but most of the information is coming from the scattering. So since we're focusing the laser beam, we can still work up at these higher concentrations, but now we can measure down to smaller particle sizes, down to a scale of 150 nanometers or 0.15 microns. So this is our approach to be able to get to the smallest possible sizes using this optical particle counting technique. The diagram you see down below is just showing that this is still a very high resolution technique. And the reason we're going to use the FX Nano in one of the measurements today is because we wanted to look for these tails, these aggregates of particles that are a little smaller than 0.5 microns. And this is going to be much more sensitive to see a few large particles, because sometimes a few large particles are an indication of some instability or perhaps the process hasn't been optimized quite yet. Now we need to get the sample through the sensor, and we use samplers that are configured different ways depending on the concentration of the sample. What you see up above here, if we don't need to dilute the system, we can just use a syringe pump and aspirate the sample up through the sensor. This is our SIS sampler. Then we have systems that can dilute the system automatically if we're working at higher concentrations. This is our AD system. We have both an AD, the auto diluter, or the APS, which has a two-stage dilution system for working at very high concentrations. The system you see down here in the lower left, this is actually the syringe sampler, but two sensors. So we can stack the FX Nano and the LE400 sensor. This will give us the widest dynamic range, down to 150 nanometers, up to 100 microns. And this is how we can measure the broadest dynamic range. In the last system you see on the lower right, we can also do online measurements using this optical counting technique, the SPOS technique. And this is a picture of one of our online systems, which we call the mini system. And if you have a process that requires continuous monitoring, this is an instrument we could utilize in that kind of situation. So those are the systems we're going to talk about today for these measurements. And now I'm going to turn it back over to Steve, and we're going to start showing some applications where we use both the microfluidizer and one or both of these sizing techniques to track the particle size reduction.
So there are two main types of applications that we're going to talk about. First is, so a lot of people know what nano-emulsions are. If you don't, it's essentially two different phases, typically a water phase and an oil phase, but it can be any two or more immiscible liquids. And the idea is to create a uniform set of droplets of one of the phases in the other. Most nano-emulsions tend to be oil in water, but you can also have water in oil or oil in oil, or sometimes there are double emulsions, which are typically water in oil in water. There are two main biopharma applications. One is active ingredient delivery. So for instance, for eye drops, you can dissolve some of a very potent active in an oil, create this nice nano-emulsion, can then be sterile filtered, and then be delivered by eye drops right into your eye. The other use for nano-emulsions in biopharma are vaccine adjuvants. And that's what we're going to be talking about today. We're going to be talking about this very specific type of vaccine adjuvant called MF59. And if you're not familiar with vaccines, I'm just going to go through real quick what they are and what vaccine adjuvants are. So vaccines are biologic materials that when you expose them to your immune system will see them and create antibodies so that you are then, when you are exposed to that material, and naturally your immune system can recognize it, and it has these antibodies which will kill materials so that you don't get the disease. However, when you are delivering a vaccine, it's not always good at triggering an immune response. So the purpose of an adjuvant is simply to trigger an immune response. And I'll talk about that a little bit more later, but it's very complicated. I'm not an expert in it, and even the experts don't always know 100% why these adjuvants work. But MF59 is a very well-studied and very commonly accepted adjuvant. It is made of squalene, which is a shark liver oil, dispersed in water. And this graph over here on the right, this talks about immune response as a function of time. And then these are three very commonly used vaccine adjuvants, and this is MF59, which typically has the highest immune response for any vaccine adjuvant. So we did a case study. This is the formulation. We used squalane, which is only slightly different than squalene. The main difference is it's synthetic versus squalene, which is actually naturally derived from shark livers, so it's a lot less expensive. And then we processed with first with the rotor feeder mixer, and then through the microfluidizer processor and measured by laser diffraction. Then after we processed it through the microfluidizer processor, we measured it with the Nicomp DLS system.
Yeah, so what we see here on the left-hand side, you see the result going from 8.5 microns. That was a measurement by the laser diffraction unit. And then after it went through one pass, you see the very steep reduction in particle size. And then from there, because of the scale, you don't see the decrease in size. So then we switch to the right y-axis, and you see the reduction in size as we do multiple passes through the microfluidizer. And on the right-hand side, you see the change between one pass in 5 passes as measured on the Nicomp DLS system. So what you see is a reduction down to 205 nanometers after one pass and down to 142 nanometers after 5 passes. You also see the reduction in the polydispersity index. That is a measure of the width of the distribution. So you can see very clearly is a very significant decrease in the size after it goes through the first pass. And then as it goes through the multiple passes, once we get to 5 passes, the reduction from 205 down to 142 nanometers. And this is the data when we ran the microfluidizer at 20,000 psi. And then the data down below, we're going to look at the data when we processed the sample at 30,000 psi. On the left again, you see the first dramatic decrease in particle size as we go through the first pass, looking at the left y-axis. And looking at the right y-axis, we see the change as we go from 1 to 5 passes. And on the right-hand side, you see as we went through the system with one pass, we were at 185 nanometers. Then after 5 passes, we would reduce the size down to 114 nanometers. So you can see at the higher pressure, we did get a better size reduction, both through 1 and 5 passes. So this is what we see analyzing the data after we go through multiple passes through the microfluidizer using the Nicomp DLS system.
So the next example, we're going to talk about our liposomes, and we recently had a webinar with Dr. Yvonne Perry from the University of Strathclyde, who is our collaborator working with liposomes, and some of the data that we're going to show in a little bit is from that webinar. If you find it fascinating, I highly recommend you check out the full webinar because she is amazing to listen to, not only because she is an expert in liposomes, but she has the best accent. So these are liposomes. They're made of these amphiphilic molecules called phospholipids, and they come in a couple different shapes and sizes. Liposomes are typically a bilayered vesicle, but you can also use these phospholipids to make lipid emulsions. And they come in all different sizes and types you can have. These are conventional. You can also make them cationic. You can also make them stealth by coating them with PEG so that they're not recognized by the body's lymphatic systems to remove them from the bloodstream as quickly. And you can also attach antibodies to these and use them as vaccine adjuvants as well. Liposomes are used for a lot of different applications, but typically drug delivery and vaccine adjuvants are the most commonly used. So the study that we're going to look at is how these two different vaccine adjuvants are used. There's a study done by Dr. Perry where the vaccine adjuvant was injected at a site, and then we varied many different parameters, including the type of phospholipid and also the particle size, to determine how quickly they disperse from the injection site, and also how quickly they are cleared from the body. So preparation of liposomes is a little bit of a process. Essentially, the first step is to dissolve the phospholipid. Usually cholesterol is used, and some actives in a solvent. And then the solvent is removed by evaporation. Then a buffer is added. The system is warmed and mixed to create this nice solution, and you can add your antigen, and you get these multi-layer vesicles, which are typically in the range of 1 to 5 microns. Then you process them through a microfluidizer processor, and you get these small unilamellar vesicles that are typically in the size range of less than 100 nanometers. So this is the first formulation which we tried. It was the phospholipid was from Lipoid. It's Lipoid S100, which is a common phospholipid. We also used soybean oil. So this is an example of a lipid emulsion. The sample was mixed for 5 minutes, and then we processed on the LV1 microfluidizer processor with the F12Y chamber at 20 and 30,000 psi. And we measured the samples on the Nicomp DLS.
So we're looking at similar plots here for processing the liposomes at 20,000 psi above and 30,000 below. As you look at the upper left, again, you see that first dramatic size reduction as we go through the microfluidizer the first time. Then as we look at the right y-axis, we see the change in size going down from about 230 nanometers after one pass and getting down to 155 nanometers on the 5th pass. And on the right-hand side, you just see the Gaussian distribution results as we go 1, 2, and 5 passes through the microfluidizer. The same results down below, but at 30,000 psi. And we see here, as we go through 1, 2, and 5 passes, we see a reduction to 214, down to 189, to 149 nanometers. So what we're seeing is a reduction in particle size through each pass, and as we operate at higher pressures, a greater reduction in the particle size, and that's what we expect. So very simple processing and very simple measurements to track this reduction in particle size as we operate through the microfluidizer at different pressures using different numbers of passes.
This is another example. We used HSPC, which is a type of phosphatidylcholine, and cholesterol. And this was done in 70 degrees C water, and it was pre-mixed with the rotor-stator for 10 minutes. And then went through the 110p microfluidizer processor at 25,000 psi for up to 10 passes. And this was analyzed by both the Nicomp N3000 and the AccuSizer 780AD. And you see these, this is really cool. You can see the premix looks cloudy, and you can see that as the particles get really small, they actually become smaller than the wavelength of visible light. So they actually become quite transparent after multiple passes through the midstream.
So what we see on the left-hand side is the results from the Nicomp DLS system. The premix is the result in pink, and then as we go shifting to the left to the smaller size ranges, we see the 1, 3, 5, and 10 pass results. So you can see the reduction in particle size as we go through multiple passes through the microfluidizer as measured using dynamic light scattering. And we can see the mean size is going from maybe at 150, 180 nanometers, and we get down actually well below 100 nanometers, down to the scale of about 55 nanometers once we get up to 5 or 10 passes. So that's a dramatic decrease in the particle size. Now, with the dynamic light scattering technique, you're seeing we're drawing these Gaussian distributions. And you might think that there are no particles greater than, say, 500 nanometers or 0.5 microns, but there actually are a few. And if you really want to catch the percent or the concentration of particles that are larger than, say, a micron, that is what we're seeing on the graph on the right. So the graph on the right is actually looking at the tails of the distributions using the AccuSizer SPOS technique. So this was using the LE400 sensor and the AccuSizer AD system. And what you see is, what about the tails of the distribution? What about those few large particles? And you can see the reduction in large particles as we go through the number of passes through the microfluidizer. And that's why people sometimes use these two techniques in combination. You're getting the mean particle size using dynamic light scattering, and then you're using the AccuSizer to determine very accurately in concentration of particles per ml how many large particles were still present. And if those large particles are an issue, then you might have some other processing step, something perhaps like filtration, to make sure you control the number of large particles down to the concentration range you know where the product is still working in some optimal way.
The third example we have is it's a similar formulation. The difference is we varied the types of chambers we processed with a Y-type chamber independently, a Z-type chamber independently, or a combination of Y-type and Z-type chambers. And then these were measured on the Nicomp N3000 and the FX Nano Dual.
So we're looking at first here, these are the Nicomp results. In the upper left, we see the Y chamber, down below the Z chamber, and to the right, the combination of two, the Z plus Y chamber. So same formulation of this pre-made, I think it's like a pre-zome that this is actually generated from our colleagues in Japan. They had found this combination of chemistry, which makes it fairly easy to create these liposomes. So the same concentration in all cases. The only difference here is which chamber and which combination of chambers were used in the microfluidizer. And so what you're seeing is the reduction from the pink down as you go down, which is the premix, and then through multiple passes through the microfluidizer. We're looking at the change in the mean diameter as measured on the Nicomp DLS system. And I think we'll see the tabular results on the next slide. So up above we see the Y chamber, and we see the reduction in size from 137 nanometers down to 65 nanometers as we get through 10 passes. In the middle we see the size reduction using the Z chamber in the microfluidizer. Here we see a quicker reduction in particle size down to 108 nanometers, and then we get down to 64, 66 nanometers after we get through 5 and 10 passes. When we use the two chambers, that's when we see an improved decrease in particle size. We begin at about 129 nanometers, but we get down to 63 nanometers with a polydispersity of 0.16 using the combination of two chambers, and that's where we get the smallest polydispersity index. So processed the same way, we get a size reduction down to the scale of 60 or 70 nanometers, and it looks like we have probably the best size reduction when we use the two chambers. And Steve, you can maybe comment on this. Sometimes it's a question of size reduction. Sometimes is it also related to the value of the sample, or what else? How else might you decide one versus two chambers?
Yeah, it's tricky. It's very often with one chamber you get the best results, and sometimes if you use two chambers you'll get slightly better results, but typically you can get within 90% of the two chamber result with a single chamber. So most of the time we recommend only a single chamber unless we're having a really hard time getting the results that the customer wants with only a single chamber, and then they'll try to.
Yeah, all we're seeing is getting from like 65 down to 63 nanometers, but if that matters, then perhaps a two-chamber approach is better. So that's what we see here. And I think on the next, sorry, go ahead.
If polydispersity was really critical here, you see that you do get a better polydispersity, or a more narrow polydispersity with the two chambers versus the one. So it's not always just the average particle size that's critical, like you said before. the PDI might be something that's also critical to the application. So, so it's another thing we might look at.
Certainly, a more narrow distribution is usually indicative of a more stable sample. Okay, and I think on the next slide we're going to look at the FX Nano results for these samples. So what you're seeing above is just one of the results, and what you're seeing is we see the size reduction. This is maybe from the 5 to 10 passes. And up above we're saying, okay, now let's zoom in on this region of these large particles. And that's what we're going to measure using the AccuSizer FX Nano in this case. So in the lower left, you're seeing the results down to about 0.2 microns or 200 nanometers. And we're showing how we can track what is the percentage or concentration of particles greater than 0.2 microns. You'll see there's very few particles greater than 0.5 microns, and that's why we chose the FX Nano sensor in this case, because the interesting data was down below 0.5 microns, hence the choice of the FX Nano. So by using the AccuSizer, we can see the real difference in those few large particles, and that also kind of traces with the size reduction. So the Nicomp is an excellent way to get the mean diameter down to these very small sizes where other techniques just couldn't measure that size range. And then when we include the measurements on the AccuSizer, that's when we get the very accurate measurement of the concentration of the tails of the distribution. And this might trigger us requiring some other processing steps, such as filtration, to make sure we reduce the amount of tails if that had any impact on the quality of the final product.
So why is this important? So we talked a little bit about how important vaccine adjuvants are, and we talked about how particle size reduction can play a role in the delivery. This graph on the left talks about how long the material that is injected subcutaneously stays at that injection site versus how quickly it's transferred into the bloodstream. So if you have an emulsion with an average size of 750 nanometers, you see that it takes a lot longer for the adjuvant to transfer to the bloodstream than with this 100 nanometer nano-emulsion. So what that means is that the amount of material that's available at the lymph node where the immune response originates, you get a much higher concentration with a nano-emulsion than you do with this larger emulsion. So we expect a much better therapeutic response to a nano-emulsion versus a microemulsion for this vaccine. And then the other factors that come into play are whether or not you're using standard liposomes versus stealth liposomes, how many hours they inside the bloodstream and avoid MPS uptake. The vesicle size is important, but also the vesicle charge, how firm the vesicles are. So if you add cholesterol and use a high glass transition phospholipid, you can make much more firm bilayers, and that can increase the time that the liposomes will circulate in the bloodstream. And you can also coat them with PEG and make them stealth. So if you're interested in learning more about this, again, I highly recommend you checking out that webinar from Dr. Yvonne Perry at the University of Strathclyde.
Yeah, and certainly the Nicomp can make these 8 potential measurements to give you this vesicle charge information.